In this module, I'm not going to stop halfway through. I'm going to ask you to pause me instead, so that um, it's not. I think this won't be otherwise it'll be a very short module. So let's define A0 as those set of points that leave I in one iterate. I'm going to show you what that looks like in a second, and it should be reminiscent of something that you've done before. What I'd like you to do next, and you're probably going to have to pause me so I don't keep going, is to iterate around that x equals 1/2. Maybe take those 3 points that you saw that iterate outside of A0, and then you know that in one step it should leave. That means escape escape. But what happens as you go to infinity? What's the long-term behavior? So pause me as you determine that, and do confer with everybody in the class and make sure that you have a common answer. So these points seriously do escape. For what you should have found is that these indeed do escape and that they converge to minus infinity. So I'm going to define A1 as a set of x belonging to the interval such that in one iterate they are in A0. So what happens to those points that start out in A1? Where are they going to converge to? So pause me if you have to think about this, but answer this collectively as a class where you think that the points in that started out in A1 are going to converge to. I'm imagining I'm unpaused, and thank you for unpausing me. I think if my family had their way, they would never unpause me. So if you have that it goes to A0 in one iterate, and you know that if you iterate forward in A0, they go to minus infinity, then A1, any x starting in A1 would also converge to minus infinity. So I can keep doing this. I can say, okay, I'm going to find those points in I that map to A0 eventually, right? I'm dropping the r here now just to keep it simple. So we are talking about the rx times 1 minus x. So if any one of those iterates in finite time ends up in A0, then they're doomed because they're all going to go to minus infinity. Then if I take the interval 0, 1 and throw out the infinite union of those sets that I'm creating, they represent the points that don't diverge to minus infinity. Those points would be those points that converge to that periodic trajectory, or they do some of the weird things you've seen where they don't converge to anything, but they don't converge to minus infinity. They don't diverge either. So all of those points are the ones that don't diverge to minus infinity. Get ready for this. There's something really weird about these leftover points. So if you haven't seen this notation before, it means this unit interval, 0, 1, with the union of these sets thrown away. So I'm removing them from the unit interval. So guess what? This is really wild. I hope your chairs have seat buckles. This is like the wildest thing ever, and you'll be so glad that you selected this class. It's the most awesome class in the world, because it turns out that set is the Cantor set. So now I've linked the Cantor set to your logistic map. The only thing left to do is now link those symbol spaces also to the logistic map, and then you have thorough, absolute bizarro world. So just to give you an intuition of why that's the Cantor set, think about what you did when you iterated. Well, it turns out that the points that ended up going outside of 1 in one step look like this. So it's this interval. If you remove that interval, that should be exactly the process that you did when you formed the Cantor set. You remove the middle third, right? So you're removing A0. Well, what happens with A1? This is going to be a little bit harder, but you can start to take a guess since I'm telling you this looks like the Cantor set. So if you're removing A1, take Excel and experimentally see which points in I go to A0 in one step. what you should find is you should find broken up intervals, right? When we did the Cantor set, we first removed that middle third, then we removed the middle thirds here. So I would hunt for initial conditions here and here, and look for those that converge to A0 in one step. So try that experimentally, and then this is going to take some time to see where that is, but after you experimented for a while, come to a consensus in class that you're going to get, if you remove just A1 and A0, you're going to get 4 broken up closed intervals left over. So please do work together, because I need you to make sure that you feel like you did this right and understood this. So this should remind you of the Cantor set process, right? We're removing the middle third, then we're removing the next 2 middle thirds, so we get 4 intervals. So pause me if you need to, so that you can play around with this. You will need to pause me. So I think this is going to take the entire class just to get to this point. So I don't want to go further than this today, especially because I'm not with you. I feel like the connection between now the Cantor set and the shift map is you're going to need me in class. So we're going to do that Wednesday. But we can actually prove that those points that don't escape, this should be I minus, not A minus, I minus A0 union A1, is exactly the Cantor set. So I'm not going to do that now. I'm going to leave some of these details now so that we can get to the main point of pulling all these things together. And I will see you Wednesday.